So today we have two speakers. The first one will be Charanjit from.
You're the first one. I'm the second.
Okay, I'm the first one. Okay, so I'm analyst from Goldman Sachs, and this is Charanjit. He's a summer employee from JP Morgan.
Let's say intern.
Intern from JP Morgan.
Yeah.
Okay, so today our workshop outline will have three parts, and there will be breaks in between. So the first one will be about analytics, the second one will be machine learning, and the last one will be about NLP. Because I believe everyone here, some are non-technical, some are technical people. So we will go through everything slowly together. Okay, so to start with, so what is analytics? So in our digital era, we have a lot of social media data and machine data as well. So that's why we are trying to find different ways to make use of our efficient computing power to make our raw data more meaningful and to support the business decision that we need to make every day. And I believe some of our attendants here are doing business intelligence and analytics at their work as well. Okay, so as you can see, the most common application for data analytics currently is to improve the customer experience and to drive the growth across business. In finance especially, we use a lot of analytics to manage risk and portfolio, and also to detect financial crimes, and for example like money laundering or bribery. We all use analytics like a lot of data. And to perform algorithmic trading, we also use a lot of analytics like in terms of technical trading and also fundamental trading. And there are a lot more and more applications for analytics. So basically, analytics is to use raw data that we collect from our business operations and also from our enterprise system to understand what happened to the business and why it happened, and also what is most likely to happen next in the future given these conditions. Okay, so there are three types of analytics. The first one is descriptive, which is to explain and understand what happened in the past. And the second type is to predictive analytics, which is to use the past data and trying to make regression to understand and to see what is the most likely thing that will happen in the future, in the near future. And the third type, which we are trying to move forward at the moment, is about prescriptive analytics, which is to recommend action to, for example, like Google about self-driving car or recommendation system from for news, financial terminals, and those kind of things. They are all prescriptive analytics. So this is an example from descriptive analytics, and I believe a lot of organizations today are making a lot of dashboard to make sense of the data that they are collecting from their business operations. The first one is about sales analytics, and the second one is finance analytics. So sales analytics, for example, they can make use of their sales data to their sales funnel data to understand how the account manager perform in the past quarters and how to set better sales targets in the future. And for financial analytics, this is a dashboard to understand the profits and also the gross margins for the company. And this is an example of predictive analytics. We have Amazon stock price forecast and oil price forecast. So every quarter, analysts from investment banks, they will make forecasting on different things in the market like oil price, stock prices, and this is a type of predictive analytics. And what companies are trying to do is they trying to either meet the expectation of analysts or they trying to exceed the expectation. Okay, so the third type is about prescriptive analytics. As we can see, is Google's self-driving car or news recommendation system for the New York Times. So they just learn your behavior, they learn your historical reading data, and then they will make similar recommendation in the future. Like they know what you like to read and they know what you don't like to read. Okay, so there are 5 techniques for analytics: the regression, clustering, classification, are three most common techniques, and recommendation system and on-sampling are the other two, but we are not covering that one today, so we'll just covering the first three. Okay, so regression. Regression is a process that you use statistics to estimate the relationship between a set of independent variables and the target variables, which we call dependent variables. So there are different types of regression. So there are linear regression and there are also non-linear regressions. And the application of regression is basically everywhere. Like we can predict economic growth, predict the GDP in the next several years, or we can forecast the sales for a company. Business process optimization, we try to increase the productivity and efficiency, increase the number of products that we are trying to make, or reduce the cost of operations. And there are more and more applications for regression. It's simple enough to understand, and for we to present to the management level. That's why regression is very favorable in terms of any kind of learning algorithm, because of the easy interpretability and also easy to implement compared to other more complex algorithms like deep learning, neural networks here and there. Okay, so there are different types of regression: linear regression, logistic. There are some that you guys may be familiar with, and there are some that are quite strange. Like the very common one is linear regression, logistic regression, and we have some other things like lasso regression, ridge regression, and stepwise. So I can check it out here. Okay, so today we will cover only. Okay, I mentioned only. Okay, so for lasso and ridge regression, basically for these two models, they allow us to take in correlated variables, because they apply a penalty scheme so that they will remove irrelevant variables from the model. Okay, but we will talk more about multicollinearity and correlated variables in the next few slides. Okay, so the next analytics technique is clustering. So clustering is an unsupervised method to group data points into clusters. So there are two types of learning. We have unsupervised learning and supervised learning. So for supervised learning, we have a set of label data for us to rely on and for our model to see and learn from. For example, like Samsung S6, the category will be under mobile phone, and TV Samsung 9 or something, the category will be under let's say household application. So there are label data for us to know which item should belong to which category, and we use that data to train our model, and we call it supervised method. For unsupervised method, we don't have any label data for us, and we need to slowly learn from the messy data. So clustering is one unsupervised method, and the point of clustering is to segregate the data points into clusters so that the data points in the same cluster are more similar in terms of characteristic attributes compared to those from other clusters. So all data points in cluster A should be similar to each other more than data point from cluster A compared to cluster B. So okay, so there are some applications for clustering that we can see, which is the first one is about customer segmentation. So for example, we have a pool of a lot of customers coming to the store, and we try to segment them into different groups so that we know how to cater our marketing campaigns and also our sales campaigns to each customer segment. This one is customer segmentation is being done a lot in retails and also organizations across the world. Another application is about social network analysis. We have, for example, Facebook. They try to segment the user of Facebook into different groups so that they know the preference and the habits of each group, and then they try to launch new features that will cater specifically to that group only. And the third application for clustering is about recommendation system. So this is also to learn the behavior of the owner user, the reading habits of owner user, for example, the user of New York Times, and then segment them into different groups and recommend them with news that cater to their favorites in the future. And there are more applications for clustering. And as you can see from the graph, okay, it's quite dark, okay, so we have a group of green data points, and after we apply clustering algorithms, we have 3 clusters, the blue, red, and the green cluster. And on the white one, we identify as the noise, which means they don't belong to any of the cluster. So there are 2 main types of clustering. There are many other types, but we only mention 2 in this workshop. So the first one is about partitioning, and the second one is about hierarchy. But we are not going in depth into hierarchy today. We just cover partitioning for now. So partitioning clustering, meaning we group data points that are close to each other into clusters, like how I just mentioned. And how do you know that how close the data points are? So how close they are will depends on the distance that between them in the space. So there are different ways that we can measure distance. For example, Euclidean distance, or we can have non-Euclidean distance. So a very common algorithm for partitioning clustering is the k-means clustering. So k-means clustering is very efficient and easy to implement. Why is it efficient? It's efficient because it's efficient because it has only ON, like for the operations. While for hierarchy algorithm, it's ON squared, which is like a lot more, which is a lot less efficient compared to k-means. That's why k-means is being used a lot in the industry for cluster, and also easy to implement. So as you can see here, actually there are only 4 steps because the last one is to repeat step 4 and 5. So firstly, we need to choose number of cluster k. So this is the hardest part of k-means clustering, which means you need to estimate, okay, so what are the numbers of cluster that I need? What is the number of cluster I need? So you have to estimate a number k in advance before you can start to segregate all the data points into clusters. So choose number of cluster k. For example, let's choose k equal 3, and then we randomly assign the data points into a cluster. So we just assign randomly customer 1 into cluster A, customer 2 B into cluster B2, and those kind of things. Like we randomly assign data point to cluster, and then we compute the cluster central. So cluster central point is like so this is the group of cluster, and we always have the leader, which is the central point. Then we try to measure the distance. Actually, shall I draw it on the board? Should I draw it on the board? I think it's better. Do you have one? It's okay.
Oh, okay. Sorry, IT guy.
Okay, so for example, we have a group of customers. Let's say we have 5 customers, and then we will, for example, okay, so now looking at 5 customers, I will estimate that, okay, I'm gonna separate them into three different groups. It's just an estimate number, so I will choose k equal 3. Then I will randomly, for the first iteration, I will randomly assign the customer into cluster. So I say cluster A will have customer A and customer B. So only two of them. So this one and this one. Then for cluster 2, cluster B, I will assign randomly. So only one customer. I don't want more. So this one gone. And for cluster C, I will assign the last two customers into cluster C. Okay, so then I will calculate the central point for these two. So for example, let's say this one is 2 and 3, then the central A will be 2 plus 3 divided by 2.5. Yeah, I just come up with numbers. Then I keep doing the same thing. Like let's say 2.5, then maybe it lies around the central point around here. Then for cluster B, I also do the same. Then I have the central, which is also this guy. For cluster C, I calculate the centroid, then I have this guy. So, okay, my drawing is quite bad. Okay, so never mind. Okay, so after I get the central point for the cluster, I will reassign the cluster again, so that the customer in the cluster will be, I will choose the cluster which has the closest distance from that customer to the centroid. For example, so maybe when I reassign, I will have this one, cluster A, this one, and this one go together. And then I have cluster B. The two just remain. Then again, I'll calculate the centroid, and then I reassign again. That's why step 4 and 5, I just keep repeating, calculate the central point, reassign the data point until the accuracy, there's no significant change whenever we recalculate the central point and do the reassignment. So now let's continue. Is there any question for K-means clustering?
You mentioned at the end that till the time there is no significant difference between.
Yes.
What do you mean by significant? Is there a percentage or?
Meaning when you recalculate the central point,
yeah,
you don't see that the data point will move to another cluster. Like the data point kind of fixed in that cluster.
okay.
It doesn't keep moving around. For example, for the first iteration, we reduce from 3 clusters to 2 clusters by putting the C guy to the first group. But if I keep doing that the same thing, I reach a point where there's no movement anymore between the data point. It's just fixed. And the difficult part about this one is to find out the K number where we reach a point when the accuracy is good and there's no more significant change in the data point if we calculate the central point again and reassign. Are there any other questions for K-mean clustering? Okay, so I will move on to classification. So classification is a supervised method to group data points into a given number of categories. So for clustering, we don't have any label data. We just randomly assign, calculate the central point, reassign, keep doing that again. But for classification, supervised method meaning we have the training data, we had a label data, and our learning algorithm will learn from the training data. So there are two types of classification. Binary classification, which means we only have two categories, let's say female or male, girl, guy, young or old. But for multi-class classification, we have more than two categories. Like for example, like different industry, we have finance, we have accounting, we have healthcare, and so on. So that's why we call multi-class classification. For application of classification, we have quite a lot as well. There's speech recognition, spam email filtering, where the learning algorithm will just keep learning which one you define as spam email, which one you define as not spam email. And in the future, whenever a new email coming in, it will automatically classify the email. It is a spam email. If it is, then it will put it into the spam folder. Otherwise, it will just put in the inbox folder. Document classification. This one we have been used a lot in the law industry and also finance industry, because there are a lot of documents to read, especially for lawyer and portfolio managers. They need to keep reading about market news, market documents, and of course they cannot read everything. So there are document classification to let them know which one they should prioritize over. And it's being used in healthcare as well to diagnose cancer and other type of illness. So there are 7 techniques of classification. I think some of you guys have already seen a few here, but today we only touch on the decision tree, which is very common, the most common classification algorithm. So decision tree, why is it a common classification algorithm? Because it's easy to visualize and interpret. And another bonus point of this decision tree is that it can accept category data, category variable. Okay, so for other methods, as you can see here, like support vector machine, random forest, neural networks, it's not very easy to interpret the result of the model. And for example, if you work in a customer facing industry, for example, like say insurance, when you reject the claim of someone, you need to explain to them, okay, why am I rejecting your claim? And you cannot bring out all these complex algorithms to explain to your customer. So interpretability is very important when you decide to do classification. And the easy way is to use decision tree. To use decision tree because it's easy for you to explain to the management level or to your customer. As you can see from an example here, this decision tree is to decide, should I accept a new job offer? So if the salary at least 50,000 USD and you say yes, then you continue asking another yes or no question. Do I need to commute more than 1 hour? If you say yes, then I just decline offer. But if you say no, then you can continue asking whether the new company will offer me free coffee. If you say no, then decline offer. If you say yes, then accept offer. So the decision tree is like you have the target variables, and you need to ask several questions along the way to decide the final outcome. It's like a flowchart with yes no question in between to decide what's the next step you should take. So any question about decision tree or classification? Okay, I will. Okay, yes.
Usually, how do you determine whether a set of data is linearly separable or non-separable?
Linearly separable or non-separable?
Yes.
Actually, okay, I don't know. Okay, correct me if I'm wrong. So, but for me, I will need to do I will need to try and error a lot of models to know whether a data set is non-linear or linear. If it is not very obvious, Like for example, if it's very obvious, like then when you do the visualization, when you do the exploration step, you see. But if sometimes it's not very obvious, so need to try and error quite a few times to see the accuracy and stuff. And also it also depends on the how we choose the variable to put in the model as well, which I will come in later on. But if you have any other idea, please also let me know.
When you say linear, meaning they are very closely clustered together.
Sorry?
When we say linear, that means they are closely clustered together, and non-linear means they are very scattered. Is that the understanding?
Linear, I mean, actually not really, because a lot of non-linear data set, they also can be divided into very clear clusters. Yeah, just that when you draw the relationship line between them, it's not a straight line, but it's more like a high level, high degree polynomial line, like something like this. It's not straight line, so it's not non-linear. But when you try to use other algorithm to divide them into cluster, it will be in very clear separate cluster.
I mean, one way to look at it is when I have a data, I can find out the mean and the max. If the max is too away from the mean, that means definitely there will be a lot of non-linearity. Just one idea.
Okay.
Yeah.
Okay. Thank you for that. I will check that one. And you have other idea?
No, like if I come, I'll come.
Okay.
I'll share it.
Okay.
But that is one way of looking.
Okay. I'll take note of that and think about that later on. Okay, so just now we have been talking a lot about analytics, clustering, classification, regression. So where does machine learning come into the play? Because how come I run all the way from doing dashboard, clustering stuff to machine learning? So machine learning is a branch of predictive analytics. It produces prediction and also recalibrate the model in real time automatically after you put the model into production. But unlike machine learning, predictive analytics still rely a lot on human experts to decide the relationship between the independent variable and the dependent variable. Machine learning is like you train it once and it will automatically learn new things in the future. So there are 5 steps. Okay, we try to summarize it into 5 steps. So there are 5 steps in machine learning model. First, we do data collection. Second is data cleaning. Third is feature engineering, which means we decide which feature we should use in our model and which one we should eliminate. I will go into that later. And the fourth one is about model selection and how we do the training, testing, validating. And the last one is tuning. Tuning is about improving the performance of a machine learning model. Okay, so first part, data collection. Garbage in, garbage out. I think everyone here already has heard about that. So a model can only be as reliable, as good as the data it is built upon. So if you fit in the model very dirty, messy, irrelevant data, it will also turn out a lot of noise and incorrect prediction. And the samples in a dataset must cover as many possible cases as possible, not just the common cases. So for example, in news recommendation system, there are a lot of different types of news. It can be politics, healthcare, business, market, finance, anything. But because I did a project in school before, and we realized that politics news take more than 50% in our daily news on New York Times. So whenever we run the model, the result will always, or most of the time, will always be biased towards politics category. So that's why the sample here must cover as many possible cases as possible, not just the common cases. So meaning it must cover maybe family issues, environment issues, gardening issues, anything else, not just politics or business or market news. And the number of samples across all classes must be comparable. Okay, so I'll touch on this point later on as well. is about imbalanced and balanced data set. And for your preference, if you want to try out at home, want to do some data analytics in your free time, you can check out the public API, where this is on free. Only thing I list here are on free. So you can go to the API, get the data and try to play around with it. Like maybe get Twitter API, Twitter data, and try to figure out what is the trending news today in Singapore. Alpha Vantage API is a API to get stock price, the opening and close price, and the volume of basically it's about finance market. So this one is quite interesting. You guys can check it out as well. Later on, I will send the slides to all the attendants here so that you can just click to the hyperlink and see.
Sorry, what is API collection? Is this the name of API?
API collection?
Yep.
Oh yeah, API collection is a GitHub page. They collect nearly 100 APIs free around the world, so that you can just go and explore. So yeah, Twitter API, New York Times, Alpha Vantage. I also get from the API collection. And if you guys don't want to use API, you guys can just go to Kaggle dataset, where they already extract the data into very nicely CSV or JSON file, and you guys can just download and run, do some analytics. Okay, so after we collect data, we need to do some pre-processing, or we call cleaning data. So whenever you get the data in, most of the time, okay, in some ideal scenario, the data will be clean nicely. You can just maybe some Kaggle dataset is already clean, quite nice, like the Titanic one. So you can just use and don't need to think about cleaning. But in reality, whenever you get data online, for example, Google API, you get the Google results, or you get tweets from around the world, they are always have some weird cases that you need to clean. First is irrelevant data. So maybe you want to analyze about the finance market in Australia, but the tweets that you get from Twitter is all over the place, like finance market in Israel, or politics in US, or healthcare services in Canada. So it's all over the place. That's why you need to look at data and decide which one is relevant to your business problem. The second one we need to handle is missing value. So in dataset, it's very common to have missing value, and this will affect the precision, the accuracy of the model as well. Character encoding. So if ideal scenario, everyone will be using nice English, but there are some languages around the world they use characters. And if in our computer we don't have the decoder for that character, it will come like very weird, all the weird characters appear in the dataset, and that's when you need to clean it up as well. Like maybe do some decoding, on the languages. We need to identify outliers and decide whether we should keep it, keep the impact, or we should remove it from the dataset. And remove duplicates as well. There are some redundant data records, and we just don't want it to mess up with our model. So after we clean data, we need to explore data, because now we have a nice clean data set. We start to explore data to see the relationships, what are the variables, the number of samples that we have. Sometimes it's too small for our machine learning model, because some model they require a lot of data points. Neural networks, deep learning, they require a lot of data points. For linear connection, not as much data as deep learning, but we still have like the more data you have, the better. The number of categories there are in the data set, is it binary classification or multi-class classification? The number of samples per class to define whether we have imbalanced data set or we have a nicely balanced data set. And the relationship between variables as well. Is it like nicely linear relationship? linear and strong leadership or polynomial over the place. So this is for data preprocessing. And then after we understand our data, we will move on to feature engineering. This one, feature engineering, the most important part is about multicollinearity. So multicollinearity happens when independent variables in a regression model are correlated to each other. Like for example, the very perfect example for multicollinearity is that in the dataset we have two variables. The first variable is temperatures in Celsius degree and the second is in Fahrenheit degree. Two of them are perfectly correlated to each other. So it's like you can just remove one column and keep Celsius. Because if you put two of them both into the model, it will become like very perfect linear relationship. So what is the and actually multicollinearity is very bad for the model because it produce very vague result. Like your model will produce very vague result. Like you don't know whether I get this result because of which variable, because they are related to each other. They have effect on each other. So when you have a result, for example, you have a result that this is a cancer, a patient with cancer. You cannot decide which factor in the patient's health record contribute to this cancer nowadays. So that's why multicollinearity is quite is very bad, and you need to be careful of this. So yeah, the consequences is unpredictable variance, misleading feature important, meaning you don't know which feature contribute to this result and whether it's relevant or not. And the last one is overfitting. So what are the possible solutions for multicollinearity? We can test the correlation between independent variables one by one. So variable A go with B to see if there is any relationship between them. Then test maybe variable A with C to see if there any relationship between them. And A with D, A with E. Just keep doing permutation like that to test the correlation between independent variables. Another way is to use when we but the testing correlation between independent variables is suitable only for dataset with not a lot of features. So if you have dataset with millions of dimensions, millions of features, testing the correlation between independent variables is not an ideal way to go about this. So that's why PCA come into place. PCA stands for Principal Component Analysis, which is a way to reduce irrelevant variables, to reduce the feature, reduce the dimension. Then after we test the multicollinearity, we will check with the feature transformation. Okay, because not every clean data is usable. It's clean, but maybe the features in the dataset, they have different value range. Like for example, in employee dataset, the salary feature will be ranging between thousands, while the age feature will be ranging around from 20 to 60. So there's a big gap between the salary value range and the age value range, and this is why we need to do feature transformation. We need to bring and scale all the variables into similar value range. So feature transformation is to modify data structure or value to enhance the ability of the model to extract information. Because if there is such an imbalance between salary and age, when you try to predict something in the future, the model will tend to bias towards the salary, because the number is a lot higher compared to small number of the age, only from 20 to 60 years old. Okay, so there are some common data transformation method, meaning normalization. Normalization is to bring the data, no matter what scale it is, to the range between 0 to 1. Third is logarithmic transformation. This is very common to apply to transform skewed data. I think if I'm not wrong, it's to transform the right skewed data to make it more normal. And we have another technique called one-hot encoding, which is being used a lot in NLP to convert categorical variable to numerical one. So I think later Jordan will touch on one-hot encoding a little bit when you do NLP. Okay, so now we have model selection. So after we choose the feature we want to use, we have a clean data set. We already transform the value range of all the variables. Now we can start to think about the model, building a model. What learning algorithm to use? How should we build the model? First, we need to decide the input and output. So what is the thing that we want to come in the model? I think this part, the input, we already done in the feature engineering. We need to see the feature that I want to put in the model, and then you need to decide the output. So what kind of output you want to see? Is it numerical? Is it categorical? Because if the output is category, category, sometimes you need to, and sometimes the model will return a numerical output, and then you need to convert the numerical output back to the categorical output. So just keep in mind that you need to decide very clear what you want to put in the model and what you want to see it's coming out. Which algorithm should we use? This one depends on the data set you have, and how should we prepare the data? How you want to split data into trend set, valuation set, validation set, and test set. Okay, so this flowchart I take from Google developer website. So this is very nicely flowchart to decide which model this person should choose. I think this is an NLP problem. Later during the NLP lab, you will see step by step from cleaning, feature extraction, all the way to model selection. But that's for the lab later. So now, if we have already got our model, we have retrained it. No, actually not. Yeah, we're not trained yet. But okay, so we have a data set. We already choose the model we want to use. Next is, how should we split the data to train, evaluation, and test? Because, okay, there are three types of data set in machine learning. The first one is training data set. This is the actual data set that you use to train the model. This is the data set that the model will see and will learn from. All the patterns, noise, outliers in this model, in this data set, the model will learn. The next type of data set is validation data set. Validation data set is there are two purposes. First is to test the data set, but at the same time it's also used to tune the hyperparameter. Okay, so the difference between test data set and evaluation data set is that test data set is a totally new data set that you use only to test the accuracy of the model. You don't tune anything with test data set. You don't train the model and you don't tune the parameters with the data set. With the test set, you just use it to test the accuracy. Only for evaluation, then you can test and you can tune the parameter at the same time. However, that is also a downside of the validation data set. Because when you use the data set to tune the parameter before you test it, it means that the model already kind of seen the data in advance. So it will also kind of learn some skill and incorporate that into the model. So usually the result, the output of evaluation data set is not very accurate and a little bit biased. So if anyone here has ever done a competition on Kaggle, you will know that Kaggle have two types of data set in a competition. So the one that they release for us to test our model is the evaluation data set. Then after the competition ends, to decide who is the real winner, who will be the leader of the competition, they will use a whole new data set behind the scene to test our model once again. Okay, so and yeah, that's why sometimes in some competition, you may be the winner when the competition closed, but when the official result released, you are not the winner anymore. You become like the second place or third place. It means because your data perform well on the evaluation set, but it's not performing well on the completely whole new test set. Okay, so that is not okay. So a lot of people they will use cross-validation method to generate multiple split of trend evaluation and test for the model. Okay, so that's why one thing you can check out is K-fold cross-validation. It's a very common cross-validation technique. Okay, so the golden questions of all the time: how to split a data set into trend, test, and validation. Well, a lot of people will follow a ratio of 80-20, but in reality, it really depends on the number of samples that you have and the model as well. So, for example, do we have another slide for that? Okay, so for example, okay, the first one, number of samples. Sometimes you don't have a lot of samples, a lot of data points in your data set. Then you need to decide, you need to think, okay, so is my machine learning, does my machine learning model need a lot of data points to train? If not, then you can shrink your trend set a little bit so that you have space for some test set here. But there are some model that will require a lot of data points to be accurate, like deep learning, neural network here and there, image data set. Then you need to plan for a very big training set to train the model before you can go to test set. So that really depends on the number of sample and the characteristic of the model that you have as well. So last step, okay, wait, so far any question yet? For on the 4 steps above. Oh.
The how to select the model.
Yes.
Flowchart, right?
Yes.
It's publicly available or?
Yeah, it's public. It's on. Actually, later I can give you the link.
Sure, please.
Yeah.
Thanks.
Okay, so anyway, any other questions?
I'm interested to know the finance applications. Would that be covered in your, like, based on what you have shared?
Yeah, finance application of the NLP,
What
or we only cover the application of finance in the NLP part, which Jordan we mentioned. Yeah, other like analytics and machine learning. If you ask, and maybe later I can address the question personally. Yeah. But in the slide we don't really have any slide that dedicated to that only.
Sorry, is it common to apply much of these algorithms to time series data as well, or is it completely separate then? And what usually are the issues when you apply this to time series apart from the auto-correlations?
Okay, so you mean which
As in,
step?
do you guys also apply commonly these
Yes.
algorithms to time series
Yes.
data?
For example, all the common steps that we need to do, like data cleaning, multicollinearity here and there, is also applied to time series data.
Yeah, maybe I can answer that. So, generally we look at time series data for machine learning, or in fact machine learning for many kind of finance use cases, right? So let's say you're trying to develop a model that can predict maybe the movement of signals for a certain like a certain asset class, for example. There are many problems when you use time series analysis, right? So what we usually see is that time is cumulative. So the data, for example, right, is cumulative, but many times, right, we don't want data to be cumulative. So that is where data pre-processing comes in. We make the data into something that is usable by our model. So another example that I can think of, right, is, for example, let's say we want to. Let's see. Actually, there's no other example. Let me think of one and I'll get back to you. Yeah.
Thank you.
Actually, another problem, very very common with time series data is that you need to decide how old of data you should use. Like because sometimes if you want to do stock movement prediction, right? If you use a data set of, it's very good. Usually it's very good if you have a data set of 20, 30 years. Like for other problems like maybe product classification or customer experience, if you have a big data set over the years, it's very good. But for some problem with time series data, for example stock movement, if you use big data set of like 20, 30 years, it may not be very relevant. Like the data set during the Great Recession may not be applicable to our current situation.
Actually, the thing is that, for example, the missing data imputation, right? So I think for finance, mostly the time series data is actually clean in the sense that it's transactional, so it's evenly spaced. But for example, when time series are not evenly spaced, then the imputation becomes a bit tricky because taking the mean of the series may or may not make sense depending on the nature of the series, right?
Yes,
So
yes.
I'm just wondering whether most of these algorithms are actually still being used for time series data as well.
It is. These are all the very principle, very principle technique. Of course, you apply these things, but you need to try. Inside these things, there are many other techniques like under tunings. There are different ways to tune the hyperparameters. So which way to choose for tuning depends on trial and error and depends on data set as well.
Thank you.
Sorry, one question. If we have time, I will just ask one question.
Yes, sure.
Okay. When it comes to deploying a trained model into that live production,
Yes.
What percentage of accuracy generally the data scientists look at? For example, right? Let's assume that there's a training model, that there's a machine learning model,
Yes.
which predicts whether a person's loan has to be approved or no. Okay. Let's assume that okay, now I've achieved 92% accuracy, for example, and then I've deployed it. But then now I have 1 million rows, and then I deployed it based on that 92% accuracy. But after a year or so, I get 2 million more rows,
Yes.
and now I get 96%. Okay, so I will deploy it. So, what is the percentage that generally the data scientists look at before they deploy a model into production? Is there a thumb rule, or they just decide, okay, this is the maximum I can hit, I'll just go ahead and deploy?
I think there's no rule of thumb for that percentage.
Okay.
Because for production environment, the tricky thing about that is that it does not only depend on the accuracy of the output,
Yeah, the
but
performance
as well. So sometimes the engineer or the scientist need to sacrifice the accuracy.
Okay.
Maybe just take 2%, 3% or something like that, just to meet the demand, the aggressive demand of the production environment. For example, there are some companies that providing real-time information, so the latency they can afford only calculate by nanosecond, milliseconds, and of course the model that they put into production need to be simple enough to meet that kind of demand. So sometimes that's why there is always an argument, the dispute between the scientist and the engineer. The scientists want the model to have as much accuracy as possible, but the engineer need the performance to have as low latency as possible. That's why there is always a fight between them, and they need to sacrifice both sides to have the final product. So there is no rule of thumb. It really depends on the other side as well.
Oh, okay.
Yeah.
Thanks.
Any other?
So if I need to model on the time series data, is there any way I can automatically, like dynamically decide what kind of time series disorder I should use for each time series?
What kind of time series model?
For example, maybe I have multiple production lines of outputs. But I would like to decide on the time series model. Is there any way I can like do it online without manually looking at individual data to decide, okay, this one should be error 1, error 2, 4, and the other one should be error ARIMA 1.
You want to take this question?
I have to finish the question.
Hmm?
probably they probably answer your question after the workshop.
Yeah, because I think both of us have not really experienced that, so that we need to discuss first, and we'll get back to you after the workshop, like after the lab, his presentation. Any other questions? Okay, so let's move on to the last type of machine learning, and then we can do NLP, exciting part. Okay, so tuning on on machine learning models we have hyperparameter. Hyperparameter is the external factor, and parameter is the internal factor of the machine learning. So on machine learning models we have hyperparameters, which is the starting point to set up for analysis. But these hyperparameters are not the same for all datasets and business cases. So maybe the same model, but for different datasets and business cases, the hyperparameters are different. And the purpose of tuning is to modify these hyperparameters to optimize the model performance. So as you can see from this box, this is an example for hyperparameters for different machine learning models. So for decision tree, hyperparameter is the number of branches that you want the tree to have. If so many branches, also not good, but very little branches, also not good. So we need to find a middle ground. K-means clustering. The hyperparameter is the number of clusters, which I mentioned before. Before we do K-means clustering, we need to choose the variable K, which is the number of clusters that we want to have. So K-means clustering. And another example is alpha value for linear algorithm. So how you define the alpha is also about tuning. So for example, if you want to improve accuracy, for example, let's say you do K-means clustering for product classification, and you see your accuracy at the moment is only 0.4, which is not a very good one. So tuning means you start to change the number of clusters. You try different K equal 2, K equal 3, K equal 4, 5, 6, 7, 8, 9, 10. You keep trying different K numbers until you see that the accuracy increase. But if you and then you notice if you just keep increasing the number of cluster K, at some point in time the accuracy doesn't improve anymore, and it will start to drop. So that's why tuning is a way for you to try and error and find what is the hyperparameter to use.
So for K-means, you can use the ELO method to kind of get a sense of what are the different Ks you can use, and you can see how the accuracy
Yes, yes.
or as the clusters increase. But are there any other techniques for the other two things that you showed for getting the optimal alpha and getting the optimal branches?
For me personally, and from my experience, mostly from trial and errors. Yeah, but if anyone here have more experience about choosing hyperparameter beside trial and error, please. Yeah, if you know. But usually it's trial and error. Like I try with different K, and you see the graph. If you keep increasing the accuracy, it reach plateau some point and it starts to drop again. So the point with plateau is just the K you should choose. Thank you.
So when do we know that you need to spend more time tuning, or when do we know you need to collect more variables? Sometimes it's a variable problem. So how do you
Actually, to collect more variable is very expensive, I would say, because if you work in organization, data is I think it's more precious than gold. Like you don't have a lot of data, especially label data. Label data, you need to pay a lot of human power to label data for you manually. So increasing